Assalamualaikum. For part 4 video, the subtopic is calculation pH and pOH, indicator, choice of indicator and titrant. Okay, next subtopic is calculation for pH and pOH. So, for pH, the formula is negative log concentration H+. To find the concentration H+, the formula is anti-log minus pH. Okay, or if you press calculator, okay, press shift log. So in your calculator will appear 10 minus, and then you include the value of pH, okay, to calculate the concentration of H+. Okay. So the higher the pH means that less acidic the solution. Okay. More to basic. If lower value of pH, the more acidic the solution. Okay, basically for pH, either we want to determine the solution containing H+ concentration. Okay. This is the pH measurement from pH value 0 to 14. So, if the value pH 0 to 6, it is acid. Okay, if 0 or 1, the acid is strong, while for 6 value of pH, okay, it refers to weak acid. pH 7 is neutral. 8 to 14 is basicity. Okay, if 14, pH 14, strong base. Okay, if pH 8, it is a weak base. For pOH, the formula is negative log times concentration of hydroxide. Okay, to find the concentration of hydroxide, formula is anti-log minus pOH. Or if you press calculator, okay, press shift log, so it will appear 10 to the minus. Okay, and then you put the value of pOH, and then you can find the concentration of hydroxide. Okay, the higher amount of pOH means that the more acidic the solution. If small amount value of pOH, the solution is very basic. So for pOH, it's like to measure the basicity of the solution. Okay, so if the concentration H+ or H3O+, okay, more than 1.0 times exponent -7 molar, okay, pH is less than 7, the solution is basic. So if the concentration less than 1.0 times exponent -7 molar, pH more than 7, the solution is basic. Okay, so this is the formula. pH negative log H+, pOH negative log hydroxide. Okay, next formula, pH and pH plus pOH equals to 14. Then concentration H+ times concentration hydroxide equals to 1.0 times 10 to the power of -14 molar. Okay, we look at the example. Calculate the pH, pOH, concentration H plus and concentration hydroxide of a 0.20 molar sulfuric acid solution. So first of all, okay, the equation, okay, you dissociate the acid into ion. Okay, so H2SO4 sulfuric acid, okay, will dissociate to H plus and sulfate ion and then balance it. So in your left side there are 2 hydrogen, so on the right side you put 2 H plus. Okay, for sulfur there 1 sulfur in left side and right side is 1. Okay, same goes to oxygen, 4 right side is 4. So the equation is balanced already. So to find the pH of sulfuric acid, okay, so there are 2 mole of H plus, okay, from the molarity for sulfuric acid 0.2. So concentration times 2. Okay, so for the concentration H plus is 0.4. To calculate, first concentration H plus is 0.4. To calculate pH from the formula, negative log concentration H plus. Okay, so negative log times 0.4 is 0.398. Here very low pH, so very strong acid. Okay, to find pOH, since the formula pH plus pOH is 14, so we have calculated earlier pH, we can determine pOH 14 minus pH. So 14 minus 0.398 equals to 13.602. Right? Next, calculate concentration hydroxide shift log minus pOH. So 10 to the power minus of pOH value, you will get 2.5 times exponent negative 14. Okay, so you can look at this question. It's quite same like question number 1. Okay, first you have to dissociate the base barium hydroxide to its ion. Okay, for example, barium 2 plus and hydroxide, and then you have to balance it. So 1 mole barium hydroxide dissociate to 1 mole barium 2 plus and 2 mole of hydroxide. Right? And the concentration have to times with the number of mole. Okay, so number 3 and number 4, this is type of monoprotic acid. Okay, first you have to dissociate the ion, nitric acid to H plus and nitrate ion, and then balance it. There are 1 mole and 1 mole, and then just calculate the pH like usual. Okay, so this question, what is the pH of solution prepared by dissolve 1 gram of barium hydroxide per liter? Alright, so to find pH, okay, you have to know the concentration or molarity. Okay, so to find barium hydroxide, the molarity, okay, from gram given, find number of mole first, gram over gram per mole. So you will get mole and then find mole per liter. Okay, so 5.85 times exponent -3 molar for molarity barium hydroxide. Okay, So barium hydroxide dissociate to barium 2 plus and hydroxide. After balance, there are 2 mole of hydroxide. Okay. So the molarity of base here, and then the concentration of H plus. So because of this is base, so you find pOH first and then pH. Okay. pOH is the negative log concentration of hydroxide. Okay. That's why you have to find the molarity. So find pOH, negative log concentration hydroxide, so equal to 1.93. Next, find pH from the formula. pH plus pOH is 14. So 14 minus pOH, 14 minus 1.93 is 12.1. Okay. Next subtopic is indicator and choice of indicator. For acid-base indicator, it will function by changing color after or very near to the equivalence point of titration. So this color change called as endpoint. Okay, the endpoint is most often detected visually. For example, during titration process, when titrant was delivered towards solution in conical flask, so in conical flask contain indicator. Okay. At one point when the titrant completely react with the solution in flask, so the signal is indicator change color to mention the reaction is judged to be complete. Okay. Next, acid-base indicator are usually weak organic acid or base that dissociate partially in water with the undissociated molecules have different color from their ions. For example, undissociated molecule of phenolphthalein is colorless and the anion is pink. So, when the indicator dissociate to its ion, so the color change. So by these changes of color of indicator, we can know from the observation of titration, okay, signal for analyst to stop titrate, okay, where we assume the reaction is complete. Indicator can be monoprotic or diprotic acid.
The acid of indicator when lost proton, so it will result and exhibit different color. Okay, for example, for this one, monoprotic acid of indicator, okay, from color A, and then when dissociate to H plus and anion indicator, it will change color to color B. Okay, this will happen when the reaction is reach endpoint where the reaction is judged to be complete. When diprotic acid, so means that there are two steps or two times changes of color. Okay, from color A, so it will dissociate to an ion indicator and 1H plus, and then the color change to color B, and then dissociate to another H plus and an ion indicator and turn to color C. So two times changes of color of indicator.
Selecting and using indicators. So choose an indicator that undergoes a distinct color change at the equivalence point. Okay, next, choose an indicator whose middle half of the pH transition range greatest color change that overlap the pH at the equivalence point. Okay, means that indicator that we choose must overlap with the pH at the equivalence point. Okay. Next, indicator color change must be detectable by normal eyesight. Okay, this is the example of acid-base indicator. Okay, for example, crystal violet. Okay, transition range. Okay, this is pH from 0.1 to 1.5. Okay, for indicator, all the indicator has its own pH range. Okay, so when we put into the indicator into the acid solution, okay, the indicator color is yellow. Okay, so it will change the color to blue when the reaction is complete. Okay, but when we put the indicator in base solution, okay, for example the crystal violet indicator, so the color is blue. Okay, and then it will change color towards yellow color when the reaction is assumed to be complete or when end point. Okay, from blue to yellow, for example, when the indicator was put in base solution. Okay, so the other example of indicator thymol blue, okay, 1.2 until 2.8, methyl yellow, methyl orange, okay, bromo crescent green. So from crystal violet to bromo crescent green, the pH range is slightly low pH. Okay, methyl red, chlorophenyl red, bromothymol blue. So the pH range is about 4.2 until 7.6. Okay, towards neutral. Phenol red, 6.8 until 8.4. Thymol blue, 8 until 9.6 for the pH. Okay, phenolphthalein and alizarin yellow. Okay, for phenolphthalein 8.3 until 10 for the pH. Alizarin yellow 10 to 12. Okay, for phenol red, thymol blue, phenolphthalein and alizarin yellow, the transition range of pH is from neutral to BC. Okay, for example, if phenolphthalein indicator, okay, phenolphthalein indicator, so the pH range 8.3 until 10. Okay, so means that between this range pH, the indicator might change color, right? So for example, the pH of the solution after reaction 8.5 for the pH. So the phenolphthalein will change color, or it will change color when the pH is 9. Okay, between this range, the phenolphthalein will change its color. Okay, so that's why to choose the indicator, we have to know the reaction between acid and base. We have to know the pH for equivalence point. So we choose the indicator near to the equivalence point. Okay, the indicator change color near to equivalence point might be 8.5, 9 or 10 if you use pH. Okay, so when we put the indicator of phenolphthalein in acid solution, so the color indicator is colorless. Okay. So when the reaction occur, when the titrant was react with analyte and the signal is indicator change color, okay, from colorless to pink. Okay, perubahan color from colorless to pink. Okay, so if the solution in conical flash is base, okay, so the color of indicator is pink, and when the reaction is complete, so the indicator will change its color from pink to colorless. Okay, it's a vice versa. You can also refer to this website for indicator. Okay, choosing a titrant. Okay, in theory, any strong acid or strong base can be used as titrant. Right, the reason is most of the reaction involve a strong acid or strong base is quantitative. So, usually, strong acid titrant can be used. But weak acid also can be used in titration. For strong acid of titrant, so the example is hydrochloric acid, nitric acid, perchloric acid, and phosphoric acid. Weak acid, for example, acetic acid, ammonium ion, and so on. Okay, for base titrant, for strong base titrant, example is strong base, sodium hydroxide, potassium hydroxide, magnesium hydroxide, and barium hydroxide. Okay. For weak base, ammonium hydroxide,